Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, India. In this, today we are going to learn the shear stress distribution. The course outcome related to this topic here, it is apply the knowledge of theories of failure, shear force and bending moment relations for analyzing the flexural stress and shear stress distributions and failure of beam sections. The Bloom's taxonomy level for this topic is apply level. So here the shear stress distribution, we are going to discuss in this session the shear stress distribution in beams or at a section. So there are various sections. One is rectangular, another one is square, I section, T sections. But here we considered a simply supported beam carrying UDL, uniformly distributed load. And we are going to discuss how the shear stress is varying across the section of the beam. So here, whenever the load is applied on the beam, along with the shear stress, bending moment also varies. So bending moment and shear stress simultaneously occurs in a section of the beam. But here we have considered here we are considering only shear stress distribution across the section of the beam. Now figure A in this is the A figure A indicates this figure. It is a simply supported beam subjected to uniformly distributed load. The simply supported at the ends there are the supports, and it is subjected to uniformly distributed load throughout the span of the beam. And now we are considered here there are two sections. One section is AB and another section is CD. These are the two sections we considered. Across that section, if you see the beam, that side view of the figure, the section AB and CD, these are side view of the section. But here, the section of the beam, and we considered the distance between two sections is the dx. And the bending moment is acting at that section. On the section AB, the bending moment is M, or moment of resistance is M. And at the section CD, the moment of resistance is M plus dm. And the bending stress at the section AB is sigma, and at section CD is sigma plus d sigma. And this section consists of a number of cylinders. That cylinder, we can see here, it is the cylinder experiencing sigma and sigma plus d sigma. And the force which you experience at section AB is AB of that cylinder. This is the cylinder. That cylinder at the AB section is the sigma. Bending force is sigma times dA. And whereas the cylinder is having a uniform cross-sectional area dA, that's why at section CD it is sigma plus d sigma times dA. Sigma plus d sigma times dA. The length of the section is dx. Now area, what is that area? The dA we consider the elemental area. For the total area is the hatching section, that is EF GH. This is the section. Now in this section here, F is the shear force and M is the bending moment. And at section AB, if we consider the section CD, F plus DF is the shear force and M plus DM is the bending moment, and I is the moment of inertia of the section about the neutral axis. The neutral axis, this is NA is the neutral axis. NA is the neutral axis. And this is the ABCD. This is the EFGH in side view, but this is the ABCD at the sections. And here the layer is, one layer is considered at a distance y1 from the neutral axis. Y1 from the neutral axis. Okay, that is the layer it is beginning. This portion is the y1 from the neutral axis. And there is another one, that is the y. That is here this neutral axis, this hatching area, that is DA, the centroidal axis is there. That centroidal axis is at a distance of y from neutral axis y. Y1 is the distance of the shaded area, starting beginning of the shaded area from the neutral axis, whereas y is the distance of the centroidal axis of shaded area from neutral axis, that is the y. Now it is required here, even is mentioned for students easy purpose to understand better. Even by passing the slides, they can read, they can understand better. Now here the shear forces, we are considering the shear stress on the portion of the AB between A, that is EFGH is there, that is the length of dx. On the AB section, the distance is distance y1 from the neutral axis. And figure C shows the cross section of the beam. If we cross section of the beam, then we can see the figure C vision. Figure C is visible. Now on the cross section of the beam, there is EF and GH. That EF is the distance y1 from neutral axis. EF is the let EF be a line at a distance of y1 from neutral axis. And now we are considering the part of the beam above the level EF line. This is the part of the beam above the level EF, that is EFGH, between the sections AB and CD. This part of the beam may be taken to consist of an infinite number of elemental cylinders. These are the elemental cylinder. This is elemental cylinder. Elemental cylinders. And each of elemental cylinder area is dA. And length of that elemental cylinder is dx. Length of the elemental cylinder is dx. Length of the elemental cylinder is dx. Now considering one such elemental cylinder at a distance y, this elemental cylinder is at a distance y from the neutral axis. Y1 is the distance. Okay, we are considering cross section of the beam, and EF is a line, is a distance from neutral axis, y1 from the distance from neutral axis. Now the y is the elemental cylinder distance from neutral axis. Now dA is area of elemental cylinder, which are very important, and dx length of the elemental cylinder. Where is the length? This is the elemental cylinder. This is elemental cylinder. And y distance of the elemental cylinder from the neutral axis. And sigma is, where sigma is the stress, intensity of bending stress on the end of the one end of the elemental cylinder, that is section AB. And sigma plus d sigma is the intensity of bending stress on the another end, that is on the section CD. One section is sigma and another section is, this is the elemental cylinder. This elemental cylinder is area of cross section is dA. At one side section AB, from your side is the AB side, from here that is the CD sign. On the AB side it is sigma, and on CD side it is sigma plus d sigma, that is the bending stress this elemental cylinder is experiencing, that is intensity of elemental cylinder. Now what is d one more important parameter is that what is the dx? Dx indicates the length of the elemental cylinder. So what we are going to do, we consider in this elemental cylinder first, what is the force is acting, then we integrate it, then it comes to the total area, that is from y to, okay, it goes to y plus d sigma, okay, from y, that is ef to, and from ef line to hg we will make it integration. Now what is the bending stress? We know the pure bending formula. What is theory of pure bending? That is sigma by y equal to m by I. From this, the bending stress on the section, one section, that is AB, that is sigma equal to m by I times y. And m plus dm is another side, that is CD side, where bending moment, that is m plus dm. This is the, on section AB, the bending moment is m. On section CD, the bending moment is m plus dm. Now, then what about stress? The bending stress, intensity of bending stress becomes sigma plus d sigma. The sigma plus d sigma on the section CD, that is, in the place of m, substitute m plus dm by I times y. Now, this bending moment on the section C side, section CD is m plus dm, and the bending stress is sigma plus d sigma. Now we are going to find out the force we need. What is that force here? Then the force equal to stress times area, elemental area. So now let us find out the forces on two ends of the elemental cylinder. The two ends of the elemental cylinder, here it is. On the side AB, now that is sigma times dA. Now on the side that is m by I times at the section, we know that sigma into dA, that is m by I into y dA. Yes, m by I, sigma equal to m by I times y. Now what is the sigma? Sigma times dA. Substitute in the place of sigma the value of, that is m by I times y. It is not value, the equation. What is the sigma? M by I times y. Substitute that m by I times y in the place of the sigma. Then that is force on AB. That is m by I times y dA. That is on section AB. And consider again force on section CD. The force on section CD equal to stress times area, that is sigma plus d sigma times dA. Now we know again formula, that is sigma equal to m by I times y. What is that m here? M plus dm by I times y. Multiply this sigma times dA. No, sigma plus d sigma into dA. What is sigma plus d sigma? That is m plus dm by I into y dA. Now one side, one of the elemental side, that is sigma m by I into y dA. Another side is m plus dm by I times y dA. So another side it is more, one side it is less. So there is unbalancing. What is that unbalanced force? The unbalanced force will come by subtracting right side force minus by minus left side force. That is m plus dm by I times y dA minus m by I times y dA. This is net unbalanced force. That equal to cancel this m plus, further simplification, m by I times y dA plus dm by I times y dA minus m by I times y dA. Now m by I times y dA, positive and negative, going to be cancelled. That is dm by I times y dA. Now this is the net unbalanced force. After getting net, this is the net unbalanced force on the elemental cylinder. Net unbalanced force on elemental cylinder, where dm is the change of moment of resistance, I second moment of area, y, distance of the element, distance of the EF layer from the neutral axis, where dA is the elemental area. Now that is the elemental net force, unbalanced force and the elemental cylinder. We want total unbalanced force. The total unbalanced force means we have to integrate with that equation, that is integral of dm by I times y dA. Integral of dm by I times integral of y dA, this dm by I, it becomes again, is the property, moment of resistance doesn't change, but integral y dA. Now what is that integral y dA? From the concept of engineering mechanics and from centroid, that is y dA is nothing but a y bar. Dm by then total unbalanced force, that is dm by I times a y bar. Now this unbalanced force is nothing but shear force. Now this is unbalanced force. That unbalanced force is causing to shear, that is a shear resistance at level between EF. What is the shear force? That means shear stress times area. What is that area? Where the length is dx and width is b. The shear stress times b dx. Tau times shear stress times b dx. That is the shear force. So this shear force or shear resistance is equal to the unbalanced force. What is that unbalanced force? Tau into b dx equal to dm by I times a y bar. Now we want shear force, then it becomes tau equal to dm by I a y bar by b dx. Now further simplification, dm by dx a y bar by IB. This dm by dx is nothing but a shear force. That is shear force times F a y bar by I into P. That is the shear stress. This is the equation. Tau into b dx equal to dm by I times a y bar. Tau equal to dm by I a y bar by b dx. Dm by dx, separation dm by dx a y bar by IB. This dm by dx is known as change of momentum per distance. That is the shear force. That is the shear force times a y bar by IB. This is the shear stress equation. This is the source formula or parametric formula for all types of sections you can apply. So this F a y bar by IB, where tau is the shear stress, F is the shear force, A, area of section of that hatching section which we considered here. This is area of EFGH. Bar Y, centroidal distance from neutral axis. Centroid of hatching area. Centroid of hatched area. Centroid of hatched area to neutral axis. I, moment of area moment of inertia. Is tau equal to FA y bar by IB. Now consider, let us discuss a problem based on how to apply this equation. So a wooden beam of 100 millimeter wide, a wooden beam of 100 millimeters wide. Okay, a wooden beam of 100 millimeter wide and 150 millimeters deep is simply supported over a span of 4 meters. If shear force at a section of the beam is shear force at a section of the beam, that is F, that is equal to 4500 newtons. Find the shear stress at a distance of 25 millimeters above the neutral axis. Find the shear stress at a distance of 25 millimeters above neutral axis. We want shear stress at a distance of 25 millimeters. Okay. At a distance of 25 millimeters from the neutral axis. That is we want. So how to start? We know the source formula, that is tau equal to FA y bar by IB. What is that area? Where A is the area of the beam above Y1. This is the hatching area. That area equal to width is 100 millimeters and the depth is 50 millimeters. 100 into 50, that is 5000 millimeters square. Tau equal to F A bar Y by I times B. We know the shear force. The shear force was given 4500 newtons. Area, that the elemental area, the hatching area, that is just now we calculated, that is 5000 square millimeters. Bar Y we need. And what about I? Moment of inertia. Moment of inertia of what? Total section. That is BDQ by 12. What is the B? Total moment of inertia. B is 100, D is 150. That's why B into 150 Q by 12. That is 28125 mm per 4. And what about B? B is the actual width of the section at a distance Y1 from neutral axis. Actual width of the section at a distance Y1 from neutral axis. At a distance Y1. This is the width. Suppose if we consider E, it is F, G, H. This EF width, that is 100 millimeters. 100 millimeters. Substitute all these values. Now bar Y, how to get it bar Y? Distance of the center of gravity of the area A from neutral axis. This is the hatching. This is the area we consider now. That area centroid to the neutral axis. How to get it? Up to EF, AF, that is A to F distance we need, that is 25 millimeters. We want this distance 25 plus 50 by 2. Bar Y equal to 25 plus 50 by 2. That is 50 millimeters. Yeah, that's it, got it. 50 millimeters. I equal to, that is 2812500 mm for 4. B is 100 millimeters. By substituting all these values in the formula, that is a tau equal to FA bar Y by I times B. What is the F value? 4500. What is A value? 5000 square millimeter. Bar Y 50 millimeters. And I moment, that is 2812500 millimeter per 4. And a B width 100 millimeters. After substituting the shear stress at a distance of 25 millimeters, that is 0.4 Newton per square millimeter. So this is the way, in this manner we have to apply this formula in real applications. When the data are here, when the data is given of a wooden beam having a width is 100 millimeters and deep is 150 millimeters. Suppose if you want at a distance of shear stress variable at a distance of 30 millimeters, we can consider it. So any distance shear stress variation. Now importance interpretation is that the shear stress is proportional to the shear force, area and also bar Y. Now this area of hatching, the where Y bar, and also it is inversely proportional to I and B. Now B is the width. If the width is more, the shear stress becomes less. In this manner, we have to apply and we have to solve the problem. So the references followed in this session, the textbooks and reference books and also web references to understand better the concepts of shear stress distribution of a section. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.